In this section, we will talk about the properties of light, namely the electric and magnetic properties of light that cause it to interact with matter. On the macroscopic level, which is what we are able to observe, there's a very different type of behavior that matter has as compared to what happens on the atomic scale. If one were to consider a series of stairs made out of bricks, it would be as if the energy associated with stepping from one level to another represents a quantized amount of gravitational potential energy. You would need to put in a certain amount of energy to go from the first step to the second step. If you didn't put in enough energy, you would not reach the second level. Likewise, you would have to put in some additional level to get to the third step or finally to the fourth step. However, it is possible to fall directly from the top level down to the ground, and that would then ultimately end up releasing that gravitational energy and turn it into the kinetic energy that would result once you reach the ground. On the other hand, if we were to look at the steps, instead of being built to form a series of stairs, but this would be built to form a ramp, the bricks would be very, very small compared to the steps that we had previously. Therefore, the surface of the ramp might appear to be relatively smooth. If the building blocks for making the ramp were indeed essentially atoms, then we would not be able to discern anything about the series of steps associated with each layer of the ramp. This is the problem associated with quantum mechanics, because there are quantized steps at each level along the ramp. It's just that the differences in energy are extremely small and not easily discerned by us up here on the macroscopic level. So, in order to explain these very, very small little things we call atoms, we need to be able to understand the concept of quantum mechanics. It turns out that one of the really important contributions that Isaac Newton made to the field of science was the fact that he was able to pass white light through a prism and found that the white light turned into a rainbow. He explained this based upon the fact that the different colors were traveling through the prism at different speeds, and so we can take advantage of this property of light and gain information about how it interacts with matter by observing the electromagnetic spectrum associated with that light. Light is in fact, or visible light is in fact just a very, very small portion of what we now know to be electromagnetic radiation. The visible light can be divided into the different colors that we know as Roy G. Biv, or red, orange, yellow, green, blue, indigo, and violet. This is in fact just a very, very small portion of the spectrum. Indeed, after violet, there is the ultraviolet region, which is sometimes split into the near and far UV. In addition, there are X-rays and gamma rays. In the other direction, on the red end, if you go down from there, you have the infrared spectrum, and this is divided in near and far IR. But then we also have radiation that we know of as microwaves and radar, and then even further we get to radio waves and the types of waves that we use for broadcasting television signals. All of these different types of electromagnetic radiation are useful in one way or another to help us understand things about the universe, and in particular, in our case, the world of atoms and molecules. Light is a form of electromagnetic radiation and has wave properties. Wave, much like what you observe on a lake or an ocean, is a movement in which there is a displacement of the media which is perpendicular to the movement of the wave. This creates crests and troughs and adopts a form that we can recognize as a sine wave. Shown here is a plot of a sine wave that is actually not moving, but to characterize this wave, we can measure the distance between the crest and the crest. This is called the wavelength and is given the symbol of lambda. That distance is actually the same as measuring the point which is halfway between the beginning of an individual repeating pattern, and so the wavelength can be measured from also the trough to the trough, which gives the same distance. It turns out that the height of the crest, or perhaps the depth of the trough, is measured as the so-called amplitude, and in the case of light is also a measure of the brightness of the radiation. Shown here is the graphic which represents electromagnetic radiation. In this case, light has two components, an electric component and a magnetic component. The electric component is represented by the blue wave, which is moving along the x-axis. The oscillations are in the y direction, and mutually perpendicular to that is the magnetic component, which is oscillating along the z direction. The important aspect of this is that the electric and magnetic components can interact with charged particles. In particular, we will be interested in how light can interact with the electrons of an atom. Another really important aspect of a wave is the relationship between the frequency that the wave passes a certain point and the wavelength of the wave. Frequency, it can be measured as the number of waves that pass a point in a given amount of time. In the case of a wave that is shown here, we have a repeating wave that then has a length of time to reach one end to the other of 1 second. The wavelength in this case is given by lambda, and this represents the repeating pattern. There are 4 individual wavelengths that occur within 1 second for this particular wave. So this would have a frequency of 4 cycles for every 1 second. The unit associated with the number of cycles per second is called the hertz and is given the abbreviation of Hz. If we write the unit for hertz in terms of seconds, it is the reciprocal second, or second exponent minus 1. Shown in blue here is another wave that has a higher frequency, so there are more cycles per second. And in fact, now we have two wavelengths within the same distance that the red had one wavelength. So for this situation, we have doubled the frequency, and so this particular wave has a frequency of 8 hertz. So it turns out there's a mathematical relationship between the wavelength and the frequency, and they are related to how fast the wave is moving. Since light is moving at the so-called speed of light, which is in a vacuum the fastest that anything can go, it turns out to be a constant, and so the wavelength times the frequency ends up being the same as the speed of light. So also, one should recognize that if the wavelength increases, the frequency has to decrease in order to maintain a constant speed. So that gives us the equation shown in the box below here, where c represents the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. That's equal to the wavelength times the frequency.